We have asked engineers to put together a Pecha Kucha presentation based on the lessons they have learned and to share projects they have worked on. Pecha Kucha is the Japanese word for chit-chat and has now become a presentation format created in Japan in 2003 by Astrid Klein and Mark Dyson. It was created as a way to share their ideas quickly and effectively. Since then, it has spread to over 700 cities around the world. Pecha Kucha presentations require 20 images to be shown for only 20 seconds each.
I'm Ahlam, a research associate at the UA, and I want you to look around the room and think how much of what you see is a direct mining product or a byproduct. The majority of the fundamental resources our way of life comes from mining. That suspension on your car or the battery on your phone, but more importantly, wind turbines and solar panels, so clean energy transition. But the extraction process have two streams of hazardous waste. One is coarse and dry, we call waste rock, and the other is fine and wet, and we call tailings. I have been working on mine waste management for the past 10 years of my career, which brings me to the coolest project I was part of. Bit of background first. So the Diavik Diamond Mine is one of the most remote mining locations on Earth, a mere 200 kilometers from the Arctic Circle. Under Lac de Gras rests one of the richest diamond deposits on the planet. Now, there are three major kimberlite pipes under the lake surface. Diamond is extracted through open pit mining, as well as an underground recovery plant. They process ore separately from each of these pipes due to their distinct characteristics. Here you see an elaborate system of dikes and drainage, really an engineering wonderland. The ore is crushed into smaller pieces, then washed with water. The diamond is separated from the crushed ore by non-chemical density-based methods. They run the concentrate through X-ray combined with fluorescent to recover the diamonds. The slurry reject is called processed kimberlite or PK tailings. An environmental impact assessment was initiated to evaluate reclamation plans and their potential ecological implications. Enter me. My contribution to the study was to figure out and conduct a representative way to quantify the evolution of water quality as tailings particles settle and water is released. To that end, first I had to determine what percentage of the tailings slurry is a solid mineral, so this solids content. This is simply done by thoroughly mixing the associated tailings, taking in a representative subsample, drying it in a 100 degrees oven for 24 hours. The finer the sample is, the more pearls you see. Then comes the characterizing the physical properties of the tailings. The most basic test is quantifying the particle size distribution. So what you see here is the hydrometer test, which helps us determine the percentage of soil particles and their diameter, particularly those finer than an average human hair. I'll tell you why that's important. But first, we have to also understand the distribution of the coarse fraction of the solids. To do that, you separate the fine fraction, then sieve the dried tailings, then determine the percentage by mass of how much of the solid fraction is finer than a certain threshold. That threshold, of course, is dimensional. Now that the fundamentals are out of the way, comes the meat, consolidation. So just like your average French press, the consolidation test is conceptually simple. Slurry is compressed with a load to a certain level, depending on what's expected in the field, which causes water to be expelled upwards and solids to settle down. Now, the twist and the uniqueness of the project was that we were tasked to investigate both the physical and geochemical characteristics simultaneously and their evolution with time. So the consolidation testing had to be done in an oxygen exclusion environment and temperature controlled environment to replicate those conditions in the field. So here we're programming the compressor that is directly connected to a walk-in freezer in which consolidation to take place. We are setting the temperature to reflect the tailings temperature in the field because that obviously matters. And can we take a moment to appreciate whoever organized all these cables? You can probably imagine all the hurdles and logistical complications in the project. So I'd like to take a moment to send a huge shout out to Christine. She has been instrumental throughout the design and troubleshooting. Christine and I go back 7 years. She's a fabulous colleague and mentor and a friend. So this is on the left, the consolidation test, where we measure how much the solids settle in response to loading and the rate at which water is expelled from the tailings due to loading. On the right, you see the geochemical duplicate, where we collect expelled water samples periodically directly from the base of the cell using that sampling bag. This is how we assess the stress deformation relationship. So for a known load or stress, we measure the deformation as well as the pressure inside of the tailings sample. And how long does it take for that pressure to dissipate? And once the pressure has dissipated, we know that that sample is fully consolidated for that particular load. Enter geochemistry. So as I mentioned, the water fluid was collected periodically at the end of each step. The expelled water was extracted and then a full suite of geochemical parameter testing to assess changes with time. And here you see all the calibration fluids and subsamples. Here we're testing the expelled pore fluid for pH. And as you can see, it's nice and alkaline, no acidity concerns. But we also confirm that with other key performance indicators, such as the potential to consume oxygen, which we call a redox potential, and electric conductivity, which is directly related to dissolved solids. Here we're measuring the alkalinity of the pore fluid, essentially their ability to neutralize acid. So it basically involves titrating fluid by adding a chemical reagent that would change color as we acidify the sample. So it was quite a rigorous, thorough physical and chemical investigation of the tailing and their water. Now, it was also very important to delineate the evolution of concentrations of dissolved metals in the water. So here you see that apparatus that we use to do that, which is called an ion chromatography. It helps us determine the concentrations of cations and anions based on their affinity to do ion exchange. A lot of things were done, but I won't have time to talk about it. But once all the lab work was done, comes the data analysis and reporting to stakeholders, and of course, disseminating to the academic community at large. I was really fortunate to be part of this project, really cool. So that's my story, and thank you all for listening in.
Hi everyone, I'm Zion. I'm an environmental engineer at Thurber Engineering here in Edmonton. Thank you to U of A's CGS student chapter for having me. My presentation today will discuss lessons learned from an ongoing geoenvironmental project that I've been managing. The site is the location of a historical pipeline release located within an active pipeline corridor in northern Alberta. Surrounding lands are within the Alberta White Zone that are generically zoned for agricultural use. Sporadic oil and gas activity can be seen around the site, along with a peat mining operation to the northeast. In 2008, the pipeline failed and released approximately 200,000 liters of diesel. The release was contained, but a large volume of diesel entered the superficial soils and shallow groundwater. Initial cleanup was difficult because of the challenging access to the site and also other active pipelines in the area. Environmental site assessments began immediately after the initial containment efforts. The shallow groundwater was observed to be mounted on a subsurface ridge within the pipeline corridor and flowed radially outwards. The groundwater flow pattern at the site made managing and modeling the contaminant in the saturated zone very challenging. The site assessments found elevated petroleum hydrocarbon concentrations in the soil and the groundwater. Additionally, a layer of light non-aqueous phase liquid known as Ahlam was observed sitting on top of the shallow groundwater table. This presented another consideration when managing the migration of soil and groundwater impacts. Addressing the presence of Ahlam in the shallow groundwater was a priority for managing this contamination. The Ahlam of the site could act as a residual source of hydrocarbons, and an automated fluid recovery system was designed and installed at the site to recover both Ahlam and contaminated groundwater for disposal each year during the summer. Part of the continued assessment and management of the site included establishing the remedial objectives. Risk-based guidelines for soil and groundwater were identified and used as the targets for remediation and used to assess the progress and success of remedial efforts. The developed guidelines had to be protective of all environmental receptors at the site. Using the objectives that were developed for the site, the spill area was assessed in multiple iterations. Auger drilling is the typical method used to conduct geotechnical and environmental investigations in Alberta. Advantages of auger drilling can be ease of execution and relatively low cost when compared to other subsurface investigation methods. The soil stratigraphy at the site was comprised of glacial fluvial deposits overlaying glacial till with interbedded sand and gravels. The groundwater was also high and near the ground surface in areas, and these presented challenges to auger drilling as the soft upper soils tended to slough into the open bores and created potential for cross-contamination between samples and the boreholes. One solution to this was to utilize direct push drilling for the investigations. Direct push collects continuous cores through a steel outer casing that is advanced with a percussion hammer. The continuous core sampling allowed for discrete sample intervals and increased sample recovery. The sample aliquots were collected using industry-accepted protocols, including using methanol field preservation and hermetically sealed containers for volatile organics. Maintaining the sample integrity through the drilling method and the sample protocols increased confidence in the collected data. Hundreds of samples are collected during each iteration of the site assessments. It would be prohibitively expensive to analyze all of the samples at a lab, so collected samples are screened for further analysis using field screening methods, using some of the instruments that are shown right here. One example is the X-ray fluorescence analyzer, and the outputs are shown on this slide. At this site, you can see two distinctive zones of elevated hydrocarbons in the vertical profile. By using the XRF, we're able to get a real-time assessment of the soil chemical composition during the field investigation. When looking at the two impacted zones from the soil, we verified it using laboratory analytical techniques. A gas chromatogram was generated for each of the zones and identified two different chemical signatures. The top signature from the shallow impacts resembled diesel fuel. The bottom resembled weathered crude oil. To evaluate the progress and the success of the remedial efforts, groundwater monitoring wells were installed at the site. Monitoring wells allowed subsurface contaminants to be assessed without additional drilling. Wells are typically installed with lockable steel casing protectors to prevent damage and risk of tampering. The groundwater at the site has been monitored semi-annually since the start of assessments. This recent photo shows a distinct L-NAPL layer still remaining at the site. Isolating the L-NAPL during fluid recovery continues to be a challenge. However, 54,000 liters of impacted groundwater has been recovered from the site for disposal. While L-NAPL has not been exclusively collected from the site, the recovery of the aqueous phase hydrocarbon impacts have also had positive effects. Petroleum hydrocarbon concentrations in the groundwater have had an overall decreasing trend at the site, as shown in these historical groundwater trend charts. Environmental site assessments have been conducted at the site with the goal of delineating the lateral and vertical extents of the contamination. This can often prove challenging due to the site conditions such as complex geology and hydrogeology, limited site access, and limited resources, in other words, budget. While the site does contain complex geology and hydrogeology and limited site access, our client did have sufficient resources to help us succeed. With the many lessons learned through the investigations at the site, we were able to fully delineate the contaminants both laterally and vertically. So in this model, you can see isolated pockets of soil impacts in various subsurface locations. These are the result of discontinuous zones of low hydraulic conductivity that are associated with glacial fluvial deposits. Using the delineated plume, a detailed conceptual site model can be developed for the site. The end goal for this site is full reclamation, which means returning the site to its original state and capability. By effectively assessing the site and delineating and characterizing the contamination, a strategic approach to remediation can be employed. And while we're a few years from getting to this image, we hope to see progress get made every single year. Thank you very much for having me, and that was my presentation.
Hello. This is how we say hello nowadays. My name is Fernanda Imamura, and I'm a third-year PhD student at the University of Alberta and part of the UACGS student chapter. And today, I would like to talk about one of the coolest projects I've been involved with. So let's see what I have for you. Let's travel to the south region of Brazil, close to the border with Uruguay. Here we have a new and not-so-busy port, a good area to incite industrial development and technology innovation, creating new jobs. During construction and operation of the site, more than 5,000 direct jobs were created. Our project consists of a complex developed to build and repair ships, oil tanks, and offshore oil platforms for the Brazilian Petroleum Corporation. This is the first dry dock in Brazil and the largest one in the Southern Hemisphere. The cost of this complex was estimated at $265 million. Petrobras was expanding its fleet of oil platforms and decided to have their own dry dock to build and repair for them and for other companies. The dry dock is a concrete construction normally located near coastal waters, and its system allows inundation and drainage of the area where the ship would be repaired or constructed. This one is 350 meters long, 133 meters wide, and 14 meters deep. The concrete slab is 1 meter thick and required 5,400 steel H-piles. The amount of steel used in this foundation is the double of the steel used in Eiffel Tower. It's a lot. The most important structure of a dry dock is the dock gates. After the completion of the construction or repair of the ship, this gate allows the inundation of the dock through large inlet valves. This is the second largest dock gate in the world and weighs 2,000 tons. Another relevant structure to be featured is the Gantry Crane, a structure that runs along the dry dock and allows to work in two ships at the same time. This giant weight is 3,200 tons and runs over rails installed at the top of the retaining structure that composes the wall of the dock. The retaining structure on the soil site is made of permanent sheet piles and tiebacks to compose a wall. So more than 1,300 40-meter long tiebacks were used in this structure. The retaining structure in the lake's face is made of sheet pile and uses slopes to help stabilization. Given the soil profile obtained by several campaigns of soil investigation using SPT, Standard Penetration Test, it was possible to design foundations of the structures, such as the slab in the dry dock area, the foundation in the gantry crane rails in the prefabrication area, the retaining structures, and the watering system. The challenge posed by this type of profile is the intercalation of sands and clays that sometimes the sampling just cannot capture. The installed dewatering system has shown some difficulties due to the presence of lenses of clay in the sand layer, something that wasn't expected once they were not captured by the sampling using SPT. Additional SPT tests were needed, but penetration tests CPT were conducted instead once we have the problem with the dewatering system. This change has allowed us to better understand the soil profile, enhancing some features that SPT could not capture, such as the clay lenses we were missing when designing the dewatering system. Until today, the most used in situ test to calculate foundations in Brazil is SPT. I can confidently say that I have never designed foundations using information from another in situ test, mainly because the Brazilian standard for foundation is based on CPT, and they only accept designs based on this test. Despite the efforts invested by many consultants and studies, nothing has changed, and it still needed to be include some methods based on other in situ tests, revisit the existing SPT methods, and prepare new ones, especially to introduce CPT into the foundation calculation routine. When verifying the foundation for this project, some existing methods based on CPT to estimate load capacity of piles were evaluated to check if it was possible to adopt when designed. But given Brazilian soils behave very different from European and North American soils, places where these methods were developed, some adjustments were needed. To verify if the calculation was good enough, information about some tested piles in the dry docks prefabrication area was taken to compare with the calculated values. Hollow steel to piles measuring 66 centimeters in diameter and 45 meters in length were designed to support the rails of the Gantry Crane. A static load test was conducted in one of these piles that was designed to carry a compression load of 195 tons force. The ultimate capacity load expected from this static test was 390 tons force, double of the design load. Calculation will be compared to this. Calculation results ranged from 424 to 702 tons force. At least one method was in some agreement with the static load testing. However, it will be necessary to apply this routine to different sites and soil strata before deciding to adopt this method in the future. This evaluation was done because as a designer, my expectation is to have a standard that embraces the foundation design calculation routine using CPT test to elevate the standard's excellence, seeing it grows with the technology, and aim to optimize budget, schedule, and materials. Not much has changed in terms of using other in situ tests to design foundations in Brazil. However, we still keep updating our research, gathering more and more information about foundations for a good data bank. We hope one day the standard will at least accept foundation design made based on another in situ test. This project was very significant in my career. It is an important benchmark for Brazil and for me as an engineer. It's good to look back and realize I have been part of something special because it reignites the passion for my profession and makes me want to be a better engineer. Thank you for your attention. I hope you have a good day.